Hello everyone. Today let's solve the problem this one Angie's binary tree. Right. So this was asked in Codeforces round 911. Right. Division 2 for the division 2. Right. So you can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Right. So what the question states here, just give me a second. 1 second, please. So yeah, here we are given a rooted binary tree of n nodes. So we have been given a rooted binary tree of n nodes. They have strictly given the binary tree itself, right? They have mentioned we have been given n rooted binary tree of n nodes with each node having a letter L or U. With each node having a letter either L, R, or this one U, right? So just keep this in mind. So sorry, this one node. So we are given a rooted binary tree of n nodes with each node having a letter L, R, or U, right? So there is a guy called Keksik that starts at the root. Keksik starts at the root. At each node he follows the direction indicated left, right, or parent U. Parent U, sorry, this has to be parent, this has to be left, right. So like this I had to mention, right? So ignore this one. I didn't read the question entirely, so ignore this one for now, right? So here this one Keksik starts at the root. At each node he follows the direction indicated left, right, and parent, nothing but the U here, right? So we can change any nodes later. Our task is to minimize the number of changes that is needed so that Keksik reaches a leaf node. Main thing is here what we need to do, they have mentioned in this sentence that what we need to do, we can change any nodes later. Here we can change this nodes letter, we can change this nodes letter, and we can change this nodes letter, right? We can change any nodes letter. Our task is to minimize the number of changes that is needed so that Keksik reaches the leaf node. In this case these are the leaf nodes, right? Left, right. So here whatever I considered this one, in this case this one, what do we call, uh, we need to determine how many changes are needed uh, to minimize the number of changes, basically, sorry, to minimize the number of changes needed so that Keksik reaches a leaf node, right? So they have given the condition that we can change any nodes later, and our task is to minimize the number of changes that is needed so that Keksik reaches a leaf node, right? So this part, I hope this is completely clear. This itself is the question. Basically we are given a rooted binary tree of n nodes, that is fine, with each letter having with each node having a letter L, R, or U, these three letters, whether it may be L, R, U, right? So here in this case, Keksik starts at the root. Keksik is the guy's name actually. Keksik starts at the root. At each node, he follows the direction indicated left, right, or parent U. This is fine. We can change any nodes letter. They have given clearly that we can change any nodes letter. Our task is to minimize the number of changes that is needed so that Keksik reaches a leaf node. Leaf node, right? So a leaf node is one with no children. So this is the leaf node. Here in this case, L and R are the leaf nodes. They are not having any children, right? So here this one is null, this one is null. Here this one is also null, this one is null. So they are not having any children here. A leaf node is one with no children. He just needs to reach, not stay at any leaf. So he has to reach either L or R. This one Keksik has to reach L and R, not stay there at any leaf, right? So that's what they have given in the question. Let me delete this one. So I hope this part is completely clear, right? Question part is completely clear. Let's come to the input here. They have clearly mentioned, see here, they have clearly mentioned here, totally we have 5 inputs here. So 3 they have given, LRU, so this one 2 3, right? Double zero, double zero again. So these are the inputs. So 1 2 3 4 5 inputs they have clearly mentioned at the beginning itself that we will be having the 5 inputs, and the output that we need to get here is 0 double 1 3 1, 0 double 1 3 1, right? I hope the question part is completely clear. I hope the question part is completely clear. Let's discuss the same thing by taking the first example in the approach, right? So within the approach, you'll understand other inputs as well, what they have given, right? So you'll understand other inputs as well, right? So I hope the question part is completely clear. What we need to do is completely clear, right? So they've given the question beautifully, right? So they have given the question beautifully, right? So now what shall we do? Let's discuss the approach. followed by the complexities, and then let's write the code. Initially, let's discuss the approach first. So let's consider first example that they have given in the question, right? So here we have been given this one. 3 is nothing but the number of nodes, and you can consider or number of nodes here. So this one, right? 2 and 3 are the leaf nodes. 2 and 3 are the leaf nodes. LRU is nothing but the letters, right? L, R, and U. U is nothing but the parent here. This is right, and this is left. This is left. This is fine. So first thing that we need to keep in mind here is we will be going with the DFS approach. We will be going with a DFS approach. Just keep this in mind. Don't get confused. Just keep this in mind. So here one thing. So we have considered. Let's move on with the step-by-step explanation first. I have considered the same first example that they've given in the question. So here T. So I have went with the tree structure here. Node 1, this one is represented by L. This one is represented by the L. Nothing but it is having the label L here. Node 1, this one I'm speaking of, right? So this 2 and 3 you can clearly see. By seeing this one itself, we come to know that this is the leaf node because they do not have any children here, right? Right. So let's move on with the further things here. So here, let me write the tree structure again just for the sake of understanding this one easily. This one is L. This one is having the label L. So here node 1 has the left child 2 and left right child 3. You can clearly see here. Node 1 is having the left child 2 and the right child 3, right? So and this is labeled as L basically, right? Node 2 and node 3 are the leaf nodes. This one. Node 2 and node 3 are the this one. What do we call leaf nodes? Because they do not have any children, right? Node 1 has label L. Node 1 has label L. This one. Node 1 is having the label L. He moves to left. He moves to left here. Node 1 moves to left. And node he moves to left basically. Then to node 2. Then to node 2, which is a leaf. Which is a leaf basically, right? Which is a leaf, right? So here in this case, to reach from node 1 to node 2, there are no operations required at all. No operations required at all. First, node 1 has a label L. He moves to the left, nothing but the node 2, which is a leaf here, which is these 2 and 3 are the leaf nodes, right? Which is a leaf. So it already reaches a leaf. It already reaches a leaf. We don't have to calculate how many number of operations needed here in this case. We have directly reached leaf here. So in this case, zero operations needed. Zero operations needed. So the final output is zero. Final output is zero. Operations needed here is zero. So the final output is quite obviously zero here in this case, right? So the output that we got here is zero, which is equivalent to the output that they have mentioned for the example one in the question. Example one in the question. So what happened now? The output that we got is equivalent to the example output, right? Output that they have mentioned for the first example in the question. So our approach works absolutely correct in this case. Our approach works absolutely correct in this case. This is easy example that I had considered. So I insist you to try out with the other example, second example or the third example, where you'll get the output 1 or 2, right? So I insist you to try out with them. You'll understand the question better, right? So don't go with the same example that I say here. So just try out with the different examples, right? So you'll get to know. You'll get to know how many this one basically how many number of operations or the minimum number of operations or the changes that is needed so that Kexic reaches a leaf node, that you'll understand clearly. For this particular example what I have took, there is no operations required at all. Kexic can directly reach from the this one, from the node 1 which is labeled as L to the left node, to the left node 2 directly, right? So here in this case the output will be 0. Output will be 0. So I hope the approach part is completely clear. Now we are completely familiar with the approach. As we are completely familiar with the approach, let's move on with the this one complexities part, right? So what would be the time complexity here? The time complexity would be big of n. Why? Because we are visiting the each node once in DFS. So we will be visiting basically. We haven't written the code yet, right? So we will be visiting the each node uh, and DFS. By making use of DFS, we will be visiting the each node once in DFS. So what will be the space complexity here? Space complexity would be big of n as well, because for the tree storage and recursive stack, for the tree storage, and we'll be going with the recursion. we'll be going with the recursion along with the DFS, right? So for the recursive stack and the tree storage overall, this one recursion stack is of the depth big of n. We know this one. We have solved several problems already, right? So uh, recursive stack takes big this one, the depth of the recursive stack is big of n. So here, um, overall for the tree storage and the recursive stack, overall space complexity would be big of n as well. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n, right? So now I hope the approach and the complexities part is completely clear. As we are completely familiar with the approach and complexities, let's start writing the code. So let's start writing the code, right? So let me come to the compiler here. First thing is we'll be going with the fast input and fast output. So let's import the input output package here. So this is fine. And let's import the utilities package as well. We'll be making use of utilities, right? So I'll just go with java.util.star. So this is fine. So the next step is we will be going with the tree node structure. Means we have to store the left and right child, right? So we have to store the left and right child. So in simple words, we'll be going with the initialization part here now. So let me go with the class main here. This is fine. Within this class, let's go with the tree node structure. So I'll be going with static. So here this will be static class node. So within this one, I'll just go with variables left and right. So this is fine. So we have to initialize this one. So this will be public node. So so this consists of the parameters left and right, nothing but I'll just go with int r. So this is fine. So let's initialize this one. This dot left equals L and same goes with right as well. This dot right equals R. So we are done with this part, initialization part. Let me come out of this one entirely. Just give me a second here. Let me come out of this one entirely. So first, as we have already discussed this one, we'll be going with a DFS, basically recursive DFS, right? So we'll be going with the recursive DFS function here to this one calculate or compute the minimum operations to reach the leaf, right? So we have Kexic has to reach the leaf, basically, right? Leaf means which shouldn't contain any children, right? So here we will be making use of the recursive DFS function to compute the minimum operations to reach the leaf, right? So let me write this one quickly. This one static int dfs. So this will be int u comma char s node, this one tree. This is fine. So within this function, so first let me go with the variable node and initialize this one to the tree of you. This is fine. So the next step what we will do here, if the current node is a leaf or if the current node is leaf, then no changes are required at all. In the first example that we considered, current node itself was the leaf. When Kexic moved from the node 1 to node 2, node 1 was labeled as L, right? When he moved from node 1 to the left node 2, there were no changes required at all. He could directly reach, right? So in that case, we have to return 0. In that case, we have to return 0. Let's write that edge case. Basically, let's make use of the simple if condition here. This will be node dot left, this is equal to 0, and node dot right, so this is equal to 0. Then we have to return, in that case we have to return 0. This is fine. And initially we have to calculate the minimum operations that is required, right? Minimum operations that is required to reach the leaf node. So here in this case, for this one line number 17, if we can't reach directly, then we are returning 0. Here we have to, otherwise we have to calculate the minimum operations, right? So for that one, let me make use of the this one variable minops here, and initially let me initialize this one to the integer dot max underscore value. So this is fine. So the next step is, if the child exists, then we have to try going left, or if the right child exists, then we have to try going right. So these are the conditions that we need to keep in mind first, right? So these are only the conditions basically. If then we can go with the recursion. within the same thing we can go with a recursion, right? So if the left child exists, then we have to try going left. So here in this case it would be if node dot left not equal to 0, then let me make use of the ops or the operations here. Ops dfs of, let me go with node dot left comma s comma 3. So this is fine. So we are just recursing on the left child. In the line number 22, this one I'm speaking of, we are just recursing on the left child because we are going with the condition if left child exists, then we are trying going left. We will try going left basically, right? So that's what. That is the reason we are making use of the recursion on the left child, or we are recursing on the left child basically. After recursing on the left child, if not pointing left, then we have to count one change. If not pointing left, then we have to count one change, right? So this one has to be if s of u not equal to l, then operations equals operations plus 1. So in our case it was equal to 1, so we went with this condition for the example 1, line number 17. Here if it is not, then if not pointing left, then we have to count one change, right? So next step here is, so we have to calculate the minimum operations, right? So minimum operations would be math dot min of, so we have to pass here minimum operations along with the operations. So this is fine, I think this is fine, I hope. So let me copy this one entirely, let me copy this one entirely. So let me paste this one, let me paste this one. So this is fine. This will be node dot right. When it is not equal to 0, we have to recurse on the right child, we have to recurse on the right child. This will be operations equals, instead of a dfs of node dot left, this will be right, right? We are recursing on the right child, this remains same, s and tree remains same. If s of u not equal to the letter r, because we are going with a condition if the right child exists, then we have to try going right, right? So if here in this case line number 29, if not pointing right, then we have to count one change. Finally we have to track the minimum operations. Here in this case this would be same thing, minimum operations equals math.min minops comma ops. This remains same, this is fine. Let me come out of this one entirely, let me come out of this one entirely. So final step is we have to return the minimum operations to reach any leaf. We have to return the minimum operations to reach any leaf. So here this would be return min ops. So this is it for the code. This is it for the logical part basically. This is it for the logical part. Now we are left with the input output part, right? So we are left with the input output part. So let's carry on with that. So we have to mention fast input, fast output, those things. So let me do one thing here, this is fine. So let's make use of throws input output exception. So this is fine. So here let me delete this one. So within this what do you call, within this main function, what we'll do first, let's make use of the buffered reader for the fast input. So I'll just go with buffered reader. So this will be br is equal to new buffered reader, new uh, input stream reader. So this one would be system dot in, this is fine, this one would be system dot in. So next step is fast output. So this will be print writer. So this one output equals new print writer, new this one will be, instead of buffered reader, this one will be buffered writer, new this one will be output stream writer. So let me copy this one instead, input stream writer. Let me paste this one and let me change the input to output. This one is fine, this one is fine. O has to be capital here. Output stream, this one instead of the reader it has to be writer. We are going with the fast output, right? So let's pass the system dot out here. System dot out. This is fine. Output stream writer. This is fine, right? So I hope this part is completely clear. Right, so we are just making use of this one, fast input and the fast output. Next, we have to read the number of test cases. To read the number of test cases, I'll just make use of the variable t and assign this one to the integer dot percent, because they are given in the input is in the numbers, right? Input is in the numbers. So this one has to be br dot read line, br dot read line, individual lines. So buffer reader dot read line, right? So this is fine. So let's make use of the while condition here. T is greater than 0. Then within the while loop, what we will do, we have to go with the number of nodes. We have to go with the number of nodes. So this will be n equals, again, integer dot percent here of same thing, br dot read line, right? Br dot read line. So we have to read the number of nodes, means we are going with the number of nodes basically here. So now one more thing, we are not going with the zero based indexing, we are going with a one based index. So we have to prepend the dummy space. As we are going with a one based index, we have to prepend the dummy space here. So I can write in this way, char s equals here. So this is fine. This is fine. This one will be br dot read line. So this is fine as well. This one to char array, to char array. So what we are doing in this line number 40, they don't get confused here. So we'll be going with a one based index, right? So we are prepending the dummy space. We are just prepending the dummy space. That's it. This space you can clearly see here within the strings, right? So we are just prepending the dummy space here, as we are going with a one based index. So we are done with this part. Next, we have to go with the tree array. As it is one index, we are going with n plus 1. So see here, we have to go with the tree array, right? So we have to store the element somewhere. So here in this case, let me make use of the variable name tree. This will be new node of n plus 1, new node of n plus 1. This is fine. So we are going with the tree array. This is one index. So next step here would be, we have to read the left and right children for each node. We have to read the left and right children for each node. So here it would be for int I equals 1, I less than or equal to n. So let's increment the I here. Within the for loop, what we will do, let's go with the string. Let's go with the string here. Let me go with the variable name parts. This one will be buffered reader dot read line. So again, we have to split. So this will be split. As we are going with a one index and we have left a space here. So split words here. So this is fine. So next, let's go with the L and R and assign them to the percent, right? So parts of 0 and parts of 1. So here I'm speaking of this one, L. So this is nothing but the left here. This one will be integer dot percent. This one will be parts of 0. And this one will be R equals integer dot percent here. This one would be parts of 1. So this is fine. So the final part here would be iterated value of the tree. Iterated value of the tree. This would be new node of L comma R. So this is it. So let me come out of this one entirely. Let me give semicolon or we'll get error. So let me come out of this one entirely. So now we are left with only these things. So we have to output the minimum operations from the root, nothing but from the one, from the one, from the root means from the one. Basically, we have to output the minimum operations from the root, and also we have to flush the output. We have to flush the output. These two things are left basically. So first thing, let's output the minimum operations from the root. Nothing but here out dot println. This one would be 1 comma s comma tree. So this is fine. 1 comma s comma tree. So let me come out of this one entirely. So this would be we are fleshing the output within this line. So this would be out dot flush, out dot flush. So this is fine. This is it for the code. This is it for the code. I hope the coding part is completely clear. Let's do one thing. Let's check whether this works or not. Before that, let me paste the this one. Let me copy paste the this one signature starter template. Just give me a second here. So yeah, here let me come here. Let me paste the signature starter template. So this is fine. You can just ignore this one. Let's focus on the coding part. So let me come here. Let me copy the input, these inputs basically that they have given in the question itself. We have to get the output 01131. Let's check whether this works or not. So here let me hit the run button. So we are getting some error. Print writer out, new print writer, this one. What? Error, parenthesis or square brackets accepted. So in the line number 52, where is line number 52? Print writer, no buffered writer. So this is fine, right? This is fine. So I have given star here. This is not required, I think. Yeah, now this looks green, right? So this is fine. Let me run this one again. So now we have many errors. Oh, 4 errors we have. Let's strictly, I mean this one. Clear everyone, every error one by one. So line number 28 cannot find the symbol static int. We have not left the space here. You can clearly see. Line number 28. Where is line number 28? So yeah, let me leave space here. This is fine. This has to work now. Let me run this one. This error is gone. Line number 36. Error cannot find the symbol DFS. So we are making use of the DFS somewhere. Let's come to the line number 36 here. Tops this one DFS. So we have not considered DFS here. Static and oh, DFS I have given in the caps here instead of the small, right? So this one we are going with the recursion, right? So here I have given capital DFS and I'm making use of this one. What do we call? Here I have given small letters, DFS in the small letters. So let me run this one. This has to work now. Yeah, we are left with one error. What error we have? No suitable method for println int char node. So this one I don't understand. What is this? Out dot println one. We are starting with a one basically, right? So this is fine. We're starting with the first one root node. So one s and tree. This is correct, right? Out dot println. This is correct. What is wrong? So we are just I mean, we just have to output the minimum operations from root, nothing but the one. Here we are going with the out dot println of this one comma s comma tree. So this is fine, right? So what is wrong here? Oh yeah, this one I didn't mention the DFS here. Uh, yeah, now this has to work. DFS of one comma s comma tree. Yeah, I forgot this one. So yeah, now let me run this one. Yeah. Now this is working. We are getting the desired output, right? 01131. You can clearly see here 01131. So one more thing. This is fine. I insist you to do one thing. So we checked for this one, right? So we checked for within the approach. I considered this one first input 3 LRU 2 3 are the leaf nodes here. So we checked with this one. So there were zero operations were required basically for the kexic to move from this one parent node to the leaf node, right? So here basically zero operations were required. So here I insist you to try it out with the second, third, fourth or fifth so that you understand the question better. We have minimum number of one operations is required here. One operation is required. So here one operation is required for the input 3 as well. I insist you to try out with the fourth one because we are getting the 3 here, right? So we need 3 operations for the kexic to move from the parent node to the leaf node accordingly with the conditions that they have given. So if you try out with a different input, so you'll come to know accordingly with the approach that I showed, you'll come to know the questions better or you'll understand the approach better so that you can write the code in your own intuitive way, right? So in your own intuitive way, it will be better if you consider other examples, right? Other examples and try it out in the same way that I showed for the that I showed in approach by considering example one, right? So I insist you to try with the different examples, right? So I hope the question part, I mean, this one, the solution part is completely clear. I mean, the coding part is completely clear. Let me do one thing. Let me copy this one entirely. Let me paste it over here and let me hit the submit button. I hope this works for all the test cases. Let's see. So this has to work. Let's see. Running on test one, you can clearly see here. So here you can clearly see the code got accepted, means whatever the code that we have written works absolutely correct, right? Works absolutely correct in this case. So here, just give me a second here. We went with the DFS, recursive DFS, right? So here you can clearly see this is related to the input output. First we went with a node. First we went with a node. This is nothing but the initialization part to make use of the left and right nodes, right? Left and right nodes in the tree. So this is nothing but we are performing the DFS. This is main part. This is nothing but the logical part. This is main logical part. This is it for the logical part. Actually, easy one, easy code, right? So this is again related to the reading and writing input. So we are making use of the fast input and this one fast output, right? Basically this is the input output part along with a bit of logic here related to this one, right? Input output itself. So main logical part is this one. We are performing the we are going with the initialization and we are performing the DFS, right? So just keep this in mind. So we are done with the this question. Basically, I hope the solution part is completely clear along with the this one approach as well as the complexities. We went with the recursive DFS strictly for this problem, right? I hope solution part is completely clear along with the approach and complexities. For now, this is it. Thanks for watching, guys.